So today, we're going to do something really cool. We're going to peek inside the brains of students and teachers, literally during a real university class. There was this groundbreaking study that used wearable brain scanners to answer a question that, let's be honest, affects all of us. What's the best way to actually learn something and have it stick? Well, the answer's kind of surprising, and it might just change how you think about learning forever.
Okay, be honest. Think back to the last lecture you sat through. Were you totally locked in, or did your mind kind of, drift off? We've all been there. You're physically in the room, you're hearing the words, but is that information actually getting in? Is your brain switched on and working, or is it more like it's on standby?
You see, for hundreds of years, the basic model for education has been pretty much the same: passive learning. The idea is simple, right? A teacher talks, and the students are supposed to just absorb it. But this new research throws a huge wrench in that idea by asking a really basic question. Is that really how our brains are built to learn in the first place?
And look, this isn't just you feeling sleepy in a warm lecture hall. It's a real, genuine cognitive puzzle. Educators have known about this passive learning problem for a long, long time. But now, thanks to modern neuroscience, we can actually see what's going on up there. So let's dive into this problem.
I mean, this whole idea of sitting students in a big room, it's not new. We're talking centuries old. More than 300 years ago, thinkers like John Amos Comenius were arguing for it because it was efficient. And he wasn't wrong. It's a great way to get information to a lot of people at once. But the real question is, have we been doing it the right way?
So, how in the world did they figure this out? Well, researchers went into an actual graduate-level neuroimaging course. And get this, they had both the students and the teachers wear these things called fNIRS scanners, which is this really cool tech that uses light to measure brain activity. This let them see everything in real time during two totally different styles of teaching. This wasn't some sterile lab, this was the real deal.
Okay, so here's the setup. They compared two groups. The first group was lecture only. Pretty standard stuff. You show up, you sit down, you listen. The second group was blended learning, and this is where it gets interesting. These students got the class materials a week ahead of time. Then, right before the lecture, they got into small groups and spent about 10 minutes trying to remember and discuss what they'd studied. So you see the difference? One group is totally passive, the other is active before the lecture even starts.
Let's break down that blended learning method, because the order here is absolutely key. Step 1, you prime the brain by looking at the material beforehand. Step 2, you recall. You actively try to pull that information out of your memory with your classmates. And only then, Step 3, do you actually get the lecture. It's all about warming up the brain and getting it in the game right from the beginning.
So, the big question, did it work? Was all that extra effort worth it? Oh yeah. The results, they weren't even close. The students in that active, blended learning group scored way higher on the tests. Their improvement just blew the lecture-only group out of the water. It's pretty solid proof that this active approach is just, well, a better way to learn.
Okay, so we know it works better. Big deal, right? Lots of studies have shown that. But this is where this experiment goes from interesting to absolutely mind-blowing. The real breakthrough here isn't that it works better, it's understanding why. What was actually happening differently inside their heads?
Because when they looked at those brain scans, they found something wild. It wasn't just that the brains in the active group were more active. They were active in a completely different way. They were running two fundamentally different learning programs. And this is the story of what they called knowledge representation versus knowledge construction.
So in that traditional lecture-only group, the brain was basically running what you could call the photocopier program. It's a passive process. It hears the information, it makes a copy of it, and it files it away. This lit up a part of the brain called the temporoparietal junction, or TPJ. Think of it like a filing cabinet.
But the blended learning group, totally different story. Their brains were running the construction site program. Instead of just filing the information, their brains were actively working with it, taking it apart, connecting new ideas to things they already knew, and building a totally unique mental structure. And this process lit up a completely different area, the middle frontal cortex, or MFC.
So let's just pause on that for a second. We're talking about two completely different ways the brain learns. The passive lecture, that just leads to a brain that records information as is. But the active method, that causes the brain to become a builder, to restructure the information in a way that makes sense to it. Every single student was literally building their own personal understanding of the topic.
And just when you think it can't get any cooler, the researchers didn't just stop at the students. They looked at the teachers' brains too. And they found this incredible, invisible connection going on. The teacher wasn't just broadcasting information, their brain was actively guiding the student's construction project.
Now, get this. In that active learning group, they found a stunning pattern. When the teacher's brain lit up in the TPJ, that's the photocopier or representation area, it literally predicted that about 8 to 10 seconds later, the students' brains would fire up in their MFC, the construction site area. It was like a neural call and response.
So what on earth does that mean? It means the teacher's brain was doing the work of preparing the information, packaging it perfectly, basically creating a mental scaffold. And then, with that slight delay, the student's brain would grab that scaffold and start its own unique building project. It's this beautiful synchronized dance happening between two minds. Okay, so this is all amazing neuroscience, but what do we actually do with it? How can we use this to learn better? How do we all switch from being passive photocopiers to active builders? Well, the study gives us some really clear science-backed tips. For all of us who are students of anything, the lesson is huge. Don't walk into a learning situation cold. Prime your brain first. Skim the material. Jot down some questions. And when you're listening, don't just absorb, actively try to connect the dots. And for anyone who teaches or presents, the message is a game changer. Flip the script. Start with an activity, not a speech. Design your lessons to be a construction site, not a library. Ultimately, what this all points to is a massive shift in how we should think about learning itself. The goal should never be just to absorb information like a sponge. The real goal, and the way our brains are truly wired to learn, is to get our hands dirty, engage with the ideas, and actively build our own understanding. And I just want to circle back to that incredible number 1 last time. 8 to 10 seconds. That's the predictive gap, the hidden rhythm of great teaching and learning. It's this powerful reminder of the deep, invisible connection that makes real learning happen.
So this kind of leaves us with one final big thought. For so long, we've treated the mind like it's a bucket that we just need to fill up with facts. But what if this research proves that's completely wrong? What if true, lasting learning isn't about filling a bucket at all, but about lighting a fire?